Okay. I'm Pavel. If you saw this plan, it says that I will speak about migration, but I believe I will speak about QEMU at all. And if you wanted to learn more about migration, you might be disappointed a little bit. I work in Novgorod State University and in cooperation with Institute for System Programming of the Russian Academy of Sciences. We started a project which used QEMU in 2010. It was a project for software analysis, and then it extended to implement deterministic replay and reverse debugging. The first implementation was for version 0.13, and now it is rebased to current version 2.1. What is deterministic replay? It is recording and replaying the execution of the program. It consists of two stages. At the first stage, we record the execution, and the second stage, we can replay the execution for multiple times. In this replay process, we can do different analysis things. Why do we need replaying for such analysis? The first aspect is that analysis could introduce overhead to the software that executes in the simulator. For example, taint analysis is known to be very heavy, and if the software will notice that it is analyzed, for example, it is malware or something, it could behave differently. The second thing is analysis of real-time applications that could be slowed down by this overhead and change its behavior. The second one is determinism. Determinism allows record such bugs like hazing bugs, which constantly change their behavior, or just avoid the setup of some complex environment by recording the execution. Our implementation has the following features. The first one is support for 2.5 platforms. These are Intel x86, 32 and 64 bits, and ARM. Our deterministic replay works on Windows and Linux hosts. It supports whole system debugging, including user level code and system level code. It also allows making different non-intrusive analysis of the system, like connecting the GDB through the remote protocol to the simulator and debugging the program. You also can do different offline analysis of the executed program. For example, logging, tracing, and so on. And log file, which is generated in the recording stage, is host machine independent, and you can transfer it from one machine to another and replay execution on different machines. Replaying the simulated system is similar to replaying the simulator itself. We divided the simulator into two parts The first part is what we are replaying. The second part is just the tunnel for data from the real world. We record all these inputs from the network, user input, USB, and put it in the replay log. In the record phase, all these inputs are connected to the simulator, and on the replay stage, we disconnect all of them and just take the data from the replay log. To make the replaying, we also had to write non-deterministic data. We also consider the block interaction with block devices deterministic because we start replaying and recording, always start them from the same state of the disks. And we also had to serialize the thread pool because multiple threads could cause race conditions. The changes we had to do are the following. We added record replay subsystem. We changed dynamic translation modules to count instructions. And we added log recording functions to the platform independent modules for input. Why we didn't use the currently existing account in QEMU? Because it was a long time ago, and we found that it has different issues, several issues. Two of them are the following. The first one is that block instructions for Intel are not working correctly in the single-step mode. The second one is that breakpoint set through the GDB is also also leads to incorrect instructions counting. My colleagues from Green Sox today asked me about it, and I rechecked this and found that these bugs are only x86 specific, and they use ARM and didn't notice them. As I said, we implemented instruction counting a long time ago. That's why we chose very conservative approach. We just increment instruction counter after every instruction execution. It's not very fast, but it works. And of course, it's the first thing to change when we fix the account. We will adopt it to our reverse execution. Hardware clock logging is pretty simple. We just write clock values into the log when the hardware clock is accessed. In the replay phase, when hardware clock need to be accessed, we just read this data from the log. We also needed the checkpoint execution by making the snapshots of the system to rewind the execution back and then execute it forward to the desired state. It is needed, it is required for the reverse debugging because reverse debugging often needs just stepping one instruction back, and we cannot restart whole system from the beginning to make just one step back. the following inputs of the non-deterministic data are recorded. They include keyboard, mouse input, network packets, audio card, I mean microphone here, serial interface, and USB devices connected to the through the lib USB. All of things above we used to implement reverse debugging. Reverse debugging is possible through the remote GDB connection, and it implements all of the commands for reverse debugging. How does it work? How does reverse continue work? Imagine the following program, which initializes the pointer, then corrupts the pointer, and then tries to dereference it. The developer wants to find this point and then issues the following commands. He sets watch point to the pointer and issues the reverse continue command. Simulator thus finds this point in 4 steps. First, it loads the snapshot, then executes, replays the execution forward, and finds all the points where the pointer is changed. Then it loads the snapshot again and goes to the last point where this watch point was hit. We tested the performance of the record and replay. We used 3 scenarios. One of them is loading of Windows XP. Second one is downloading of the file from the internet. And the third one is compressing the file. We got the following results. We have the reverse execution has very small amount of replay log is very small, and it is on the same level as other known implementations like VMware, which was published several years ago. And recording overhead, it seems to be very big sometimes, and it is because conservative and non-effective instruction counter. To this moment, we found several bugs in QEMU core by using reverse debugging, and not by using the replay, and prepared patches to be submitted for all of these functions. These are already applied patches with which contains bug fixes mostly on migration. And this one is what can you get from the reverse execution? One of the possible benefits is the deterministic debugging of new virtual devices implementation. On the previous slide, you could see the patch for ROR instruction, which we noticed after the execution of the several billions of instructions on loading windows. If we haven't the replay debugging, we could not find this bug. But determinism allowed us to re-execute this path again and again, and finally figure out the reason of the bug. Another thing of how can you use it is reverse debugging through the GDB of the user code, or even the system level code, including the kernels. And the third one is implementing your own offline tracing tools, or using the existing ones like Wireshark. Our plans include upstreaming all of this code to the master branch. These changes include the bugs in the core, in the QEMU core that were not already submitted, and the patches for reverse debugging. We also plan to work on improving performance of the QEMU. The first thing of improving is changing the icon. And we also started development of the testing framework for the QEMU, for the reverse execution, to perform regressive testing of it, because rebasing it to new versions often cause new bugs that we want to detect and find as soon as possible. Thank you to your attention, and I'm ready to answer the questions.
These bugs that you found in the bug list, did you just find the reason for them while...
These ones?
Yes. Or did you find them using the reverse debugging? Did you find this bug or you fix the bug?
Oh, we found these bugs using replaying of the QEMU. Some of them occurs under certain conditions, and replaying allowed us to find them faster. And these are patches already applied to master branch. I answered your question.
Yes. Oh, and I also have some patches. I would like to ask you to read the recording patches, because I myself have been recording disk keyboard outputs, and I know other people that are interested in recording. So more there's other users that of recording for that.
We already sent preliminary version of recording patches to mailing list, and now we are polishing them and refining them to be applied. Yes?
Would it be possible to remove all checkpoints so we can fix the size of the rug? You said it.
That one. This checkpointing is optional feature. We can specify period of checkpointing in command line, but if we specify no period, there will be no checkpoints at all.
But we can keep the, for example, the last 3 checkpoints only.
We haven't implemented this yet. It also in plans.
Okay. We've actually got an implementation of that at some point might go upstream. Because there's 2 different ways of doing that.
I'm assuming the logs can only be created when you're in full emulation TCG mode, not accelerated.
Sorry?
I'm assuming to generate your log files you have to be running in TCG.
Yes, we implemented it only for TCG, not KVM.
How much speed difference is there when you're doing a replay scenario versus full speed?
This is slowed down for replay compared to full-speed simulation.
That depends on how far away from the checkpoint you are, how many checkpoints you took, and whether you're going.
This is without checkpoints only.
So you could actually run backwards in real time, but the chances are you're not going to hit every instruction, right? You're just going to go.
Mm-hmm. What do you do about serializing the threads? How do you manage to do that for deterministic replay?
We register. We have a queue of threads that thread tasks that has to be executed, and this thread pool adds tasks to this queue, and when we execute one of the tasks, we put it to the log, information about it to the log. And in the replay, when we find the information about task in the log, we trying to find it in the queue or wait until it appears in the queue.
If application uses a random number generator, right, and take the path, chooses the code path depending on the results, can you replay the same scenario?
Yes, we can replay random generators because they usually depend on system time, I think, or something like that. We record all such inputs to replay them. Or what kind of random generator you mean?
Well, for example, new CPUs have instruction to generate random number, right?
Yes, I understand. We replay TCG code when such instructions will be added to TCG. It will take some kind of random source value, and when it will be implemented, we will log this source value, and it could be replayed.
So you mean the random generator generates basically the same number?
If we replay it, it will generate the same number.
Have you got a patch for that now?
Emulations there?
No, I don't know that there's a patch for.
Yes, I don't know about it. I know we read timestamp counter of the Intel and other processors. They have that. And when the random instructions will be added, we will record them too.
Yeah, there are some security applications that basically prohibit any decrypt. So not all the applications,
We develop replay in such a way that application shouldn't notice that it is replayed.
Do you think it's possible to implement this in accelerated mode with KVM or not at all?
I think it is possible, but it is not our goal because it we will have to manage with MSR or system instructions. It's too much work to do compared to TCG.
And how are you planning to do automated testing of these?
We have now we have idea only with simple cases by generating some inputs and recording the execution and replaying the execution then. And we plan to insert some tracing calls into the simulator to control the correctness of the execution.
When you replay, do you capture the output to...
No, we don't capture output at all, because it depends only on input and the source program, the simulated program.
So I meant, do you, for instance, if an Ethernet packet is sent during record, do you send it again during the replay?
During the replay, we do not connect to the real network, so the packet will be just dropped. Yes. So no more questions, and I think the time is out. Thank you.